All right, so what we are trying to do is find the area underneath the function x squared from the interval 0 to 1. So x squared is a parabola, but I just only drew it from 0 to 1. And the goal is that we're trying to find that area. So we're going to do that by breaking it up into these sub-intervals and then find the area of the rectangles that are underneath. Okay, so this says use the rectangles pictured to estimate the area. To get the heights, you're going to plug these x values into the function. That makes sense. It's like an input-output thing. Now I made each sub-interval 1/4. Each one of these is 1/4 in length. And we have 4 sub-intervals, which means there are 4 rectangles. The first one kind of ends up being nothing, but just go with it. It's still a sub-interval, so it's still there. Here's where I like to use the highlighter, is to highlight the heights, because I think it helps with like visualizing. If you don't want to highlight, you don't have to, but this is the first rectangle. It's a non-rectangle. There's sort of nothing there. This is the height for the next one, and then the next one, and then the next one. But the point is there are 4 of them. And we're going to plug into the function x squared to get the heights. So this first one is just 0. 0 squared is 0. The next one would be 1/4 squared. What would that give us? 1/16. This is 1/2 squared. That would be 1/4. And then this is 3/4 squared. That would be what? Yeah, 9/16. Good. So how do you get the area of a rectangle? Base times height. All right, so let's do the first one. What is the base? This distance here, hint, I kind of wrote it, 1/4. All right, so it's 1/4 times the height, which is 0. And then we're going to add up the next one. So we're finding this area right here. Now there's actually something for me to color in. That one would be 1/4 times 1/16. Plus the third one would be 1/4 times 1/4. So that's actually a square. And then the fourth one would be 1/4 times 9/16. Now for the rest of these, I'm going to write it out the abbreviated way, because if all of the sub-intervals are uniform, and what I mean is they're all the same, you can factor that out. Do you see how they all have a 1/4 in them? You would put 1/4 out front and then just add up the other 4 numbers. And I usually get asked, hey, Ms. Cole, do I have to write that 0? Technically, no, but here's my argument for keeping it. There are 4 sub-intervals, so you should have 4 numbers added up. And it's a way for you to check that you got them all. Does that make sense? Like, I know it's 0, but I'm not going to have the argument with you. If you're like, I just don't want to write it, then that's fine. Now, if you type that in the calculator, you're going to get 0.218. And this is called a left Riemann sum. And why do you guys think it is called a left sum? Yep, you're taking the heights from the left side of each sub-interval. Is it an underestimate or an overestimate of the true area? It is an underestimate. Do you see all these gaps here, all this part that we're missing? All right, so if your function is increasing, like this one is, then it's going to be an underestimate. Now, if we had a function that was decreasing, so I usually just set my pencil on the paper. If the function is decreasing like this, and you take the heights from the left side, that would be the further up side, so that would be overestimate. So let's try the next one. Same function, same sub-intervals, except this time we're going to take the heights from the right side of each of the sub-intervals. So this one would be 1/16, this one's 1/4, this one's 9/16. It's exact same as we did in the other problem. And then this is 1 squared, which would just be 1. So we'll just write this one the abbreviated way. So again, and you can only get away with that if all the sub-intervals are the same. If they're all different, you have to list them all out individually, right? But we're going to put 1/4 out front. That's the length of the sub-intervals, and then add those heights together. 1/16 plus 1/4 plus 9/16 plus 1. And this is the area that we found. If you want to shade all of them in, again, you don't have to, I'm just showing you. This is the area that we're finding, adding all of those up. So if you type that in the calculator, you would get 0.468. I'm just giving you that so you have like a reference for a decimal, because I know like you don't know what this is just off the top of your head. And that is called a right Riemann sum, because we took the heights from the right side of the subintervals. And so if we're trying to find the actual area under this graph, is that under or over estimate? It is over. So if your function is increasing, the right sum is an overestimate. And if your function is decreasing, the right sum will be an underestimate. And again, here, I'll just illustrate it for you. Here's a decreasing function. If you take the height from the right side, it's lower down, so that's going to be an underestimate. Are we all good so far? Okay. Again, I told you this looks like a lot of pages, but the concepts aren't that bad, so we'll get through it pretty quick. All right, now the rectangles are halfway in between, or the heights of the rectangles, I should say, are halfway in between. So if you want to highlight those, again, I think it just helps to visualize. And it's still the function x squared. I haven't changed that. If from here to here is 1/4, what is halfway in between? Good, that's 1/8. 1/4 is 2/8. You can just count by eighths. So this would be 3/8. A half is 4/8. This would be 5/8, 6/8, 7/8. And to get those heights that we highlighted, you're going to plug those into the function. Again, the function is x squared. So if you take all these and square them, what are you going to get? Like for 1/8 squared. Yeah, they're all going to be 64ths, right? 1/64, 3/8 squared would be 9/64. We're just like practicing all our perfect squares here. 64s, thank you. Now this does get people because they want to put a 1/8 out front. The length of the subinterval is still what? It is still 1/4. You don't want to put a 1/8 out here. Do you see how each of the bases of the rectangles is still 1/4? All right, so it's 1/4 and then times 1/64 plus 9/64 plus blah, blah, blah. And if you type that in a calculator, you will get 0.328. And again, I'm just giving you that for frame of reference, because I know this doesn't really mean like a hill of beans to you, really. Like, at least that you have like a number to think about. Now, underestimate or overestimate is very difficult to tell for this, so I'm going to go ahead and tell you this one. This is called a midpoint sum. Everything in math is either named after the person that came up with it, like Riemann or L'Hopital or whatever, or like it is exactly what it sounds like, which is nice. All right, so midpoint sum. So if your graph is concave up, it's going to be an underestimate. Concave down, it's going to be an overestimate. All right, and I'm not real good on explaining why that is, but it has to do with the way it bends and like where the midpoint is. Like, you can Google it. I'm not real great at explaining that, but trust me, it's true. All right, so is this one going to be over or under? Well, is this graph concave up or concave down? It is concave up, so it's going to be an underestimate, but a very slight underestimate. Would you agree that this is a better estimate of the true area than either of the other ones we did? Yeah, because the part that's like over and the part that's under are going to kind of like counterbalance. All right, and then the last type of sum we're going to do is called a trapezoidal sum. So instead of a rectangle, you're going to have a trapezoid. This is your formula for the area of a trapezoid, which you do have to know. So I don't know if you want to put like some stars next to that. It's 1/2 height and then base 1 plus base 2. So you add the bases together. And the thing is, when you do these, all the trapezoids are on their sides. So this is the height. You see what I'm saying? So the length of the subinterval, that's the height. And then these are the bases because all the trapezoids are on their sides. Okay, so I still like to highlight these. Again, I know you're like this, she's repeating herself, but I think it helps. I'm just going to write them all out. This was 0, 1/16, 1/4, 9/16, and 1. All right, so we're going to write this out the long way first, and then I'll show you the abbreviated way. Again, you can only write it out the abbreviated way if all your subintervals are the same. So if they're different, you can't get away with writing it the shorter way anyway. So let's do the first trapezoid. It will be 1/2 times the height, which is the length of the subinterval. That would be 1/4. And then you add the bases together. So it would be 0 plus 1/16. So that's the first one. 1 down, 3 to go. Again, here's your formula. It's 1/2 times the height, which is 1/4. And then you add the two bases together. So we're looking at the second trapezoid. What are the bases for that one? 1/4. Good. 1/16 plus 1/4. Halfway there. Next one. 1/2 times 1/4, and then add the bases together. We're looking at the third one. So it'll be 1/4 plus 9/16. And then the last one, 1/2 times the height, which is 1/4, and then 9/16 plus 1. So what do they all share in common that we could factor out? 1/2 and 1/4, okay? And then watch me point to this. Do you see how the 0 only got used once and the 1 only got used once? But the 1/16 is in there twice, and the 1/4 is in there twice, and the 9/16 is in there twice. The end ones only get used once because they're on the end, but these are shared. Like this one's on the first one and the second one. Do you see what I'm saying? Okay, so it would be 0 plus double the 1/16 plus double the 1/4 plus double the 9/16, and then plus 1. So it is a good deal shorter. So the first and last one just get used once. All the ones in the middle get used twice. And again, just so that you get a decimal for this, it is 0.343 if you were to type it in the calculator. So this, oh, good. Truncating. I always truncate. I don't ever round because it's just not worth it. So this is a trapezoidal sum. And it is an average of the left and right sums. I don't know why you would find the left sum, find the right sum, and then average them to do that, but just FYI, it is. And if it's concave up, you have a very, oh, I shouldn't tell you this. I should ask you guys this. This graph is concave up. The trapezoids are very, very slightly where? Over or under? Very, very slightly over. And if your graph were concave down, it would be very, very slightly under. So this is a very slight over. So whenever you do the trapezoidal one, I usually just draw something concave up or concave down and you can see it. Like here's concave up. You can see that your trapezoids would be very slightly above it, right? Here's concave down. You can see that your trapezoids would be very slightly below it. So like trapezoidal, I don't have any problem with. And then I just always remember midpoint is the opposite of it. So like this one I can figure out visually, and then I just remember this one's backwards. So, all right, so are any of those better than others? Better to the true area? Trapezoidal, or I would probably go trapezoidal. I think I can't actually remember which one is technically closer, but probably one of these two. But what would make the estimates more accurate? More subintervals. Which I know is annoying. It was annoying to do it with 4. Can you imagine doing it with 1,000? But do you see how the more you have, the better estimate it would make it, because you would have less and less error. Okay, let's just try a couple more and then I'll give you a brain breaker. Find the left, right, midpoint trapezoidal sums for this function on the interval 0 to 6, 3 equal subintervals. So if you go from 0 to 6, that's 6 units. Divide that by 3, what will be the length of each subinterval? 2. So at first glance, oh, I only need to plug in 0, 2, 4, and 6. Well, but for midpoint, you need the numbers in between. So we're going to need to do 0, 1, 2, 3, 4, 5, and 6. Let's just make a table right here. We'll plug them in real quick. It'll be nice and painless, all right? All right, so if you plug in 0, what do you get? 36, good, 0, 36. If you plug in 1, that'll be -1 plus 36, so 35. 2, that would be -4 plus 36, so 32. 3 squared is 9, so -9 plus 36, 27, good. 4 squared is 16, that'll be what, 20? 5 squared is 25, -25 plus 36 would be 11. And then if you plug in 6, you're going to get 0. What I usually tell people to do is circle the subintervals. It's from 0 to 2, from 2 to 4, and from 4 to 6. Let me zoom in a little bit. So circle the subintervals. So first we'll do a left sum. So the length of each subinterval is 2. And then you're going to take the value on the left. So look at your interval from 0 to 2. Which is the number on the left? 36, right? That's all you got to do. Plus, now here, watch me point to it. Here's the next subinterval from 2 to 4. 32 is the one that's on the left. And then the last one from 4 to 6, 20. I'm not going to make you simplify that down, but let's say whether it's an over or underestimate. What's happening to these values? What are they doing? Decreasing. If you have something that is decreasing and you pull from the left side for your heights, it's the higher up side, so that would be an overestimate. All right, a right sum. Again, each subinterval is 2 units. Now we're going to pull all the numbers from the right side of the subinterval. So which 3 would those be? Good, 32, 20, and 0. And I would write the 0. I strongly recommend it because see how in the directions it says 3 equal subintervals? That means you should have 3 numbers added together. So it's a way you can check. So again, the function's decreasing. If you take the heights from the right side, they're lower down. So that would be under. All right, midpoint. The length of the subinterval is still 2. Don't change that. And then you're going to take all the midpoints. So that would be all the numbers you didn't use yet. So 35, 27, and 11. I'm going to come back to that one because I usually just do trapezoidal and then I remember it's the opposite. So your formula for a trapezoid, it's 1/2 times the height. So 1/2 times 2, the length of the subinterval. You're going to use the first one and the last one once, and then all the ones in the middle twice. So it'll be 36 plus double the 32, double the 20, and then the 0 just once. You going to make it? We'll do number 8, and then I'll give you a break. So is this graph concave up or concave down? Well, it's a parabola that's upside down. So what do you think? Yeah, concave down. It's doing something like this. So your trapezoids would be very slightly where? Under. And so if that's under, this is over. I'm not going to lie, that's how I always remember it. I just do this one and then I'm like, well, that's the opposite. All right, so let's look at number 8. The table is made for you. Use the 4 subintervals, and if you want to circle them, I think that's not a bad idea. These are the 4 subintervals. Find a left Riemann sum. You cannot write this in the abbreviated way. Why not? They're not even. 0, 3, 8, 10, 16. They're not even. They're not uniform. Okay. So your first subinterval is from 0 to 3. That's a length of 3. And what did it say? Left or right? Left sum. Which is the number on the left? 10. 3 times 10. Plus. Now we're looking at the second subinterval from 3 to 8. What's the length there? 5. Good. And that's why they're not uniform. From here to here is 3, but from here to here is 5. All right, and then the number on the left is 12.5. Good. All right, and then the next one, from 8 to 10 is 2. The number on the left, perfect. I love it. All right, and then the last one, 10 to 16 is 6. The number on the left is 28. All right, you don't have to simplify that down, but it does say under or overestimate, and then that scary word justify. Okay, what's happening to the values in the table? What are they doing? Increasing. And I'm not gonna lie, I usually just do this. Just draw something that's increasing. We did a left sum. So the left side would be what? Under. Do you see how this is lower down than the under? So you're gonna say underestimate because, we have to do a because it said to justify. Underestimate because f of x is increasing and this is a left sum. You have to say that the function is increasing and we did a left sum. And then B, use the 4 subintervals indicated by the table to do a trapezoidal sum. You have to do all 4 of them separately because the subintervals are not uniform. You're going to be okay. Here we go. 1/2 times the height. Again, they're on their sides. So the height is the length of the subinterval. So the first one will be 3. And then you add the bases together. So 10 plus 12.5. 1 down, 3 to go. All right, what's the next one going to be? 1/2 times what? Good, from 3 to 8 is 5, and then 12.5 plus 17.5. Plus, I know this is a lot to write out, but I actually kind of like these because like once you get the hang of the pattern, you just write it out and that's your answer. All right, 1/2 times 2. And then 17.5 plus 28. And then the last one, I ran out of space and I have to come down here. 1/2 times 6, 28 plus 46. All right, so far we have done estimations of the area under the curve. All right, all of these are not true exact answers. They are just estimations. Definite integral where we're headed here gives the exact area under the curve. I should be really specific here. Gives the exact area under the curve. So it's like the true perfect answer. Now we said the way we make our estimations better is by having more subintervals. So this means that your number of subintervals, oh, what is that? Good. Well, we say approaches infinity because you're not allowed to say that something equals infinity. Yes, infinite subintervals. Awesome, perfect. So subintervals approaches infinity. So here is how you write it. It is your integral symbol, which looks like, you know, on a violin, or does anyone play a string instrument? You know, it looks kind of like that. What's that? In 6th grade? Okay. Well, like that little S kind of shaped thing. From A to B, which just means from the start of your interval to the end, and then it's f of x dx. What all of those parts stand for is f of x is the height. Remember how we plugged into the function to get the height? Those things that we highlighted, we plugged into the function. So f of x is the height. Dx represents the width. Or the base. I guess I should have said base. Whatever. Base times height. It's the rectangle. You get what I'm saying? Base times height. dx is, do you know delta x? Did you guys ever see this delta x with the triangle? Change in. So when you're looking at your subinterval, like this is the change. So it's the base of the rectangle is what that is. Okay, thank you for heads nodding. So actually, let's set up a definite integral for this. This would be the integral from where to where? 0 to 1, so integral 0 to 1. And what was the function that we were looking at there? Good, it was a parabola, x squared dx. Let's type that in our calculator and we'll get the true exact answer. We did a bunch of estimations. Now the way that you type this is in the math menu. So everybody hit math. Well, let me see if some of you guys from last year remember this. It's number what? Do you guys remember what number this is? 9. It's math 9. If you forget, it says f int. Oh, and didn't I show you guys f8 derive? We did derivatives. We did a couple of them. Anyway, math 9, and then you go and type it all in. Integral 0 to 1 x squared dx. Enter, and it will like literally spit out the answer. Do you get 0.33333333? Okay, so what is that? 1/3. That area is perfectly 1/3. This. Don't you think that's cool? I think that's cool. I know I'm a math nerd, but if you're in Calc BC, you should be too. It's 1/3. So do you see how close our estimates were? Like that's why I wrote them out in the decimals for you. So you can see now these ones weren't very good. And yeah, exactly. Yeah. And do you see like these ones weren't as good over and under? Well, it depends on how much error you're willing to put up with, you know? All right, all I want you to be able to do with these is set up the integral, and then we'll type it in the calculator to see it. So this is the integral from where to where? 1 to 5. And then that function is a parabola, so we're going to need an x squared. It's also upside down, so I'm going to need a negative. Ooh, we're going to review transformations. It's been a minute since you guys have done that. How would you get this center point? It went right how much and up how much? Oh, good. X minus 3 squared plus 4 dx. What's that? The left and right. Yeah, and then this. Oh, the stretches and shrinks. Yeah. All right, so this one would be integral from where to where? Good, negative pi over 2 to positive pi over 2. And is this sine or cosine? That's cosine. Cosine of x dx. I do want you guys to type that one in because I like this one. I think it's interesting. So do math 9. And we're going to do negative pi over 2. Pi is seconds, and then the little caret key, the exponent key, is right below clear. So negative pi over 2 to positive pi over 2, cosine of x dx. And you need to be in radian mode. Make sure you're in radian mode. But it comes out to, do you get 2? Isn't that cool? I think that's cool. You can disagree, but I'm right. That's so cool. So whenever you have sine or cosine, each one of these bumps is 2, which means each one of these is worth 1, which is just a nice thing to have in your back pocket if you know that you can answer something like that real quick. I don't know. I think that's cool. Indeed. All right, now these are ones, we're going to set up the definite integral, but they're ones that you would have to split. So this one, we're going to go, and this is the interval you're given, from -1 to 2. So we would want this area here. So from -1 to 2. But I'm going to have to set it up as 2 separate integrals. The first one's going to have to go from -1 to where? Where am I going to have to split it? At 0. So from -1 to 0 is going to be underneath that line, which is x plus, it went up 1, good. And hold on a second, because I think I did that a little quick. So from -1 to 0 is the part underneath the line, and then you would have plus, and we're going to have another integral picking up where that one left off. So it would go from where to where? Yeah, good. 0 to 2. And that is another upside down parabola. So negative x squared plus, what did it go up? Plus 4 dx. Hey, that's cool. I'm scared I'm going to put the dx. There are times you can get away with that on the AP exam and times that you can't. Their rule is, what they'll do is put a dx at the end of the line that you have written. And if it will still make sense with it there, they'll take it. And if it won't, then they won't. Most often it won't make sense. Do you get what I'm saying? So try to remember to put the dx there. All right, this one we're going to go from negative 2 to 3. So this part. And I do realize, like, yeah, it's a triangle, but just go with the calculus because I just want to talk about if there's a discontinuity. You do have to break it there for the discontinuity. You can't integrate through the discontinuity. Okay, so we're going to have to split it at 2. So this would be integral from where to where? Good, negative 2 to 2. And that line is negative x plus 3 dx. Plus, and then you would have integral from negative 2 to 3 of the same thing. So the point I'm trying to make is you can't integrate through a discontinuity. Does that make sense? Like if there's a break or an asymptote or a hole, then you can't integrate through that. All right, this next thing, I copy and pasted from the College Board that you can read that if you want to, okay? Do you guys remember these from last year, this pattern? These sort of, okay. It's one of these things that is not actually hard, but it just looks so complicated that it just always frightens everybody so bad. Turn your paper to the side and I'm gonna write this over here. What we have is limit as n goes to infinity. And what that means is we want the number of sub-intervals to be infinite. Is everyone still with me? Because we said that, right? You want infinite sub-intervals. So that makes sense. And then you have this sigma. Does anyone know what sigma means? Like, what does that mean? You're at the top. Sum up. We're adding up all the rectangles. Good. So we want an infinite number of sub-intervals, and then we want to add them all up. So starting at 1, they picked K. It could be any letter of the alphabet. It really doesn't matter. From K to N, and N is infinite. It is f of A plus delta x K. A is where you start. So whenever you're looking for this pattern, like that's where you start. And then this is times delta x at the end. Delta x is the change. So like how long the sub-interval is, like what the change is, okay? I realize that looks like Egyptian. Let me do a problem and it'll make a little bit more sense, all right? Limit as n goes to infinity. That means we want infinite sub-intervals. Sigma, that just means that we want to add them all up. It's going to be ln of x. The stuff inside of here is what the variable is. So inside of your integral, you're going to have ln of x. And then dx, essentially, you just need to figure out what the boundaries are on the integral. So here's where you start. 2, are you guys seeing that there? Because that's literally all it is. So your lower boundary is 2, and your delta x is 5. That means the change is 5. So if you start at 2 and the change is 5, what's the upper number going to be? 7. And that's it. That's literally all it is. And they use like 17,000 different symbols to try and say that. Let's try another one. You're trying to write it as an integral. So this one will be integral of, and all this that I'm circling is going to be the variable. So it will be 2x dx. So that's the function. Where are we starting for this one? -2, and then the change is 3. So if you start at -2 and you change by 3, that will be 1. Here, you don't have to write this down, but let me just make up another one really quick, because this one's a little bit different, just to make sure that we've got it. Oh, what do I want to make this one? Give me a number. Give me another number. All right, this would be integral of what? Sine x dx. I was just going to do this real quick. If you don't want to write it down, that's fine. I just made up another one. Sine x dx. Where would you start? 3, and the change is 5, so the upper boundary is 8. Do we feel like we got it? Because this one's a little different. So do you see how in all of those these match? Like this is 5 and this is 5, and here this is 3 and this is 3. Do you see how it doesn't match in this one? So the only part I can circle is the k over n, because that matches. So it's like 1k over n, so that's what matches. So this will be integral square root 1 plus 3x. So the x, and I'm sorry, then dx. The variable is just that part that I circled, because the whole thing didn't match. So where do you start? Because doesn't it feel like you want to say 1? You have to look at just the part that's circled. You're starting at 0, because it is nothing plus k over n. Do you see how there's nothing there? I know you're like, no, of course we don't see it, Ms. Cole, because there's nothing there. It's nothing plus k over n. So you're going to start at 0, and then your change is 1, 0 to 1. I did not make that problem up. I got that from the College Board website. And when I read that, I thought it was evil. And I was like, well, I guess I better put that on the notes then, because if that's what they had on there, we better do it too. Here. All right, so the next thing we're going to look at are your integral properties. I'm going to use like, I guess, poor notation here, but every single integral should have an f of x dx in it. But just for the sake of space and writing these out, I'm going to not do that, right? So integral from a to a, and again, it should say f of x dx. I'm going to leave that off. Integral from a to a would be nothing. That's like the integral from 2 to 2. Well, you didn't accumulate any area under the graph because you didn't go anywhere. Does that make sense? Okay. Integral from a to b, and again, it should say f of x dx, just I'm kind of abbreviating. Integral from a to b is negative integral from b to a. I always think of it like a trip. Like if you drive somewhere and then you drive backwards, it's the opposite way. So if you reverse the boundaries, just put a negative out front. All right, and then integral from a to c would be integral from a to b plus the integral from b to c. And I'll explain that as like a road trip as well. It's like if I was to go from here to there, but I did a road or not a road trip, if I did a rest stop like halfway in between, like you go from A to B and then you go from B to C, like SE has another. Yeah, that is why I like integrals better than derivatives. Not that derivatives don't make sense, but this is just so like concrete to me. It's more like you can reach out and touch it and make sense. Kind of thing. Like rectangles, I get that. You know? All right, so we're given integral from 1 to 4 x squared dx is 21. From 1 to 4 x dx is 7.5. 1 to 4 of just dx is 3. I always tell everybody, put a 1 inside of that one, because it's not nothing, it's a 1. Kind of like if you see an x all by itself, it's a 1x. All right, so what would this one be? I reversed the boundaries. So instead of 1 to 4, it's 4 to 1. Well, this one was 21, so this would be negative 21, anti-21. For this one, I recommend writing it all separated. If you don't want to, fine, but I'm going to, so you have to watch anyway, right? This would be 2 times the integral from 1 to 4 x squared. And you're allowed to take the coefficient and put it out front. You can't put a variable outside, but you can put the coefficient out. Minus 5 times the integral from 1 to 4 for x dx. That's the second part right there. And then you want to think of that 4 as 4 times 1. So this is plus 4 integral from 1 to 4 of 1 dx. That's why I always say put the 1 there, because it's not nothing. And then we're just going to substitute in all the values that we were given there. So this would be 2 times what? Yeah, that part is 21 minus 5 times 7.5 plus 4 times 3. Whatever that is. Oh, there we go. Thank you. I want it to be good because, you know, I take a picture of this and then post it. So if anyone looks at it, I want it to be right. So, all right, we're going to use this graph to answer the questions. We need to find the area under the curves. You will need to be able to find the areas of basic shapes. And by that, I mean squares, rectangles, triangles, trapezoids, circles, semicircles. You're not going to have to find the area of like a pentagon. Does that make sense? Okay, but you aren't going to be given those formulas. You have to know that. All right, so here we go. This is a triangle. What is the area formula for a triangle? 1/2 base times height. The base is 5. The height is 4. So that triangle is worth 10. Units squared. We don't usually put units with these. All right, this is a semicircle. That's half of a circle. A whole circle is pi r squared. So a half a circle will be 1/2 pi r squared. And the radius is what for that? Good, 3. So that would be 9/2 pi. Whatever that is. Oh, actually, it will be negative 9/2 pi. Why is it negative? I almost forgot the most important part. I love that you come with me on my vocabulary. It's below sea level. It's like a de-accumulation. It's an un-area. It is area that is being unaccumulated, but it's below sea level. This is how my brain does it. And then the last one, another triangle. So 1/2 base times height. The base is 1, the height is 2. So that little guy is worth 1. And then once you do all that, the hard work is done. Now you're just going to use them to answer the questions. Integral from -5 to 0, 10. Integral from 0 to 6. Yep, negative 9/2 pi. I made the first 3 just finding this. From 6 to 7 is 1. Just don't forget what you're actually doing. The integral means the area under the graph. Okay. Now from -5 to 7, that's the whole thing. So you'd have to add all those up. So 10 plus 1 is 11, and then minus the 9/2 pi. Now this one has an absolute value. So it's -5 to 7, so it's the whole thing, but the absolute value means you want to treat them all like they are positive. So it would be 11 plus 9/2 pi. And then this last one is 0 to -5. So watch me point to it. Here's 0, here's -5. If we go from 0 to -5, we're going backwards. So -10. 15 and 16 are the exact same kind of problem that we just did, except you have to draw the graph yourself. It's the only difference. But I believe in you, and I know you can all draw a graph, all right? So we're looking at 1/2 x plus 2. That's a line. This is like welcome back to Algebra 1 class here. Do you remember y equals mx plus b from like a million years ago? Yeah. So you're going to start at 0, 2, and then your slope is 1/2. So up 1 over 2. So you want to start out, just graph the function. And then we want the area from -2 to 4. So here's -2, here's 4. This is the area that we're looking for. So what shape did we get? It is a trapezoid and it is on its side. So this is the height. Okay, just like, or turn your head. Okay, so trapezoid is, what is the formula? What does it start with? Good. 1/2 times the height. Now again, this is the height. So 6, good. And then you add the bases together. This one is 1, and then this one is 4. Let's simplify that down just to keep our skills. I know I told you don't have to, but let's do it anyway. 15, good. And then last one, this is absolute value. You want to figure out where the point of the absolute value is going to be. And it's going to be at whatever makes that 0, because we're trying to find where it hits the x-axis. So if you set this equal to 0, what would you get? Good, -4/3. That's -1 1/3. That'll put us like right about here. So that's the center of the V. It's going to go like this. And then what I would do, honestly, is just plug in the -3 and the 0. That'll give you the ends of it. Okay, it's going to look like little kitty cat ears. So if you plug in -3, what's that going to give you? Think it through. If you plug in -3, good, it'll be -5, and then you absolute value it and get +5. So -3, 5. And then if you plug in 0, what do you get? 4. So the graph looks like this. And I mean, the graph goes on forever, but we're only finding the area from -3 to 0. So these two little kitty cat ears are like mountains. I don't know. They're both triangles, though. That's what we're finding the area of. I basically put this on here so we could practice fractions. That's really why I did it, because we're going to have fun with fractions in just a second. Triangle is 1/2 base times height, and we have 2 of them. So we're going to have 1/2 base times height plus 1/2 base times height. If you want to kind of set it up. It doesn't matter which triangle you do first. Let's just do this one first, because it's closest to 0. Now, this is at -4/3. So what is the base of that? 4/3, good. All right, so the base is 4/3. What's the height of that one? Good, 4. So that's the first one. Now the base for this is a little trickier. So if this is 4/3 or 1 1/3, this would be 1 2/3. Are you coming with me on that? So that would be what, 5/3? And then the height for that one is 5. And again, I'm going to simplify it down just so we can practice the fractions. Because what if it was multiple choice? Then you'd have to do that. You just multiply the numbers together. 4 times 4 is 16. 2 times 3 is 6. And so what would this one give us? 25/6. Ooh, they're both 6. That's great. We can add them together. So that would be 41/6.